Hey there, Grade 7 robotics engineers! Welcome to this explainer of our core lesson, Sensing, Application Task Video Overview. And for those of you keeping track of our specific module ID, we are looking at STEM Robotics Unit 04, Lesson Pack 03, Sensing, Application Task Video Overview. I am absolutely thrilled to be your guide today as we decode exactly how robots actually interact with the physical world around them. We're going to dive deep into the mechanics of sensing, decision-making, and real-world applications, pulling from the very best data from the CSTA, Arduino, Carnegie Mellon Robotics Academy, and NASA. So let's just jump right in.
Let's kick things off by busting a massive myth right out of the gate. Do robots sense the world the exact same way you do? The answer is a resounding no. It's incredibly easy for us to anthropomorphize machines, basically treating them like they have human qualities. It's totally natural to think that when a robot stops right before hitting a wall, it actually sees the wall the way we do. Or we might think a robot vacuum is scared of falling down the stairs when it backs away from a ledge. But here's the reality. Robots do not possess human intuition, feelings, or sight. No matter how smart or autonomous they might seem on the surface, it's an illusion. An illusion created by brilliant programming.
Think about human senses for a second. We use complex biology, our eyes, ears, skin, combined with incredible brain power and intuition to instantly understand the context of a room. You can walk into a space, smell something burning, hear a faint hum, and instantly know, okay, a machine is overheating. Now let's look at the reality of robotics. Microcontrollers, like the ones used in your Arduino boards, rely entirely on raw, hard data. That data flows through very specific electrical pathways called analog input and digital pins. They don't feel the warmth of a fire or see the beauty of a sunset. They simply measure voltage changes. Literally, just a high or a low electrical signal on a digital pin. And honestly, that is their entire universe. To truly wrap our heads around this, let's look at how the Computer Science Teachers Association defines the field. They state that computer science is the study and human-centered practice of using data, algorithms, and computing systems to solve problems. So what does this mean for our robot? It means a robot doesn't magically develop human-like instincts. It doesn't choose to avoid a wall because it doesn't want to crash. It stops because you, the engineer, designed a computing system to solve the specific problem of crashing. You use data and algorithms to make that happen. Ultimately, the machine is just a tool executing your process.
All right, let's move on to Section 1, Gathering the Hard Evidence. Microcontrollers translate physical world changes into readable data. I want you to think of sensors as a robot's private detectives. When something physical happens out there in the real world, say the distance to an object changes or the ambient light drops in a room, the sensor captures that physical event and translates it into measurable electrical signals. Now, the detective doesn't judge the evidence, right? It just collects it. The Arduino microcontroller then reads these electrical signals through its analog or digital pins. That electrical signal, that changing voltage, is the hard evidence the robot uses to understand its reality. Without those detective sensors, the microcontroller is completely blind and totally isolated from the world.
Which brings us to Section 2, Application. Claim, Evidence, Reasoning.
Imagine an autonomous rover driving straight toward a brick wall. To make this work safely, we use the Claim, Evidence, and Reasoning framework. First up, we need input, which acts as our evidence. In this scenario, that's the raw data constantly streaming from an analog distance sensor. Maybe it's an ultrasonic ping bouncing off the wall and echoing back. Next, we apply the model, or the relationship. This is the logic you actually program into the board, if the distance is less than our safety threshold. And finally, we have the output, which is our conclusion. Then, stop servo motors. You take the input evidence, run it through a relational model, and trigger a mechanical conclusion. That exact loop is literally what stops those wheels just inches before a catastrophic crash.
Now, that relationship model we just talked about, in computer science, that's known as an algorithm. An algorithm is simply a precise sequence of instructions or model for a computing system to process data and make a decision. Think of it like a strict, unchangeable recipe. This algorithm acts as the robot's brain. It is the absolutely crucial bridge that turns raw environmental evidence, like that ultrasonic ping, into a definitive, safe mechanical decision. Because without the algorithm, the robot has a bunch of evidence but absolutely zero idea what to do with it.
Let's dive into Section 3, Limitations and Human Checks. Now, we can't just cross our fingers and assume our algorithms will work flawlessly 100% of the time, because, let's face it, the real world is incredibly messy. There are potential system uncertainties outlined in Arduino's engineering documentation that you're definitely going to face. For instance, you might experience sensor noise, which gives you false or jittery readings. It's kind of like trying to listen to a radio station tuned to static. Then there's environmental interference. A sudden shadow passing over a room can completely trick a light sensor. And imagine trying to navigate a dark room with a flashlight that has a dying battery. Well, that's exactly what low-power design constraints can do to a sensor. All of this creates serious uncertainty in a robot's automated conclusion. Your robot might decide to slam on the brakes when there's no obstacle at all, or, terrifyingly, just keep moving right into a wall when there is one.
And because hardware has limitations and algorithms can be flawed, the CSTA PK12 standards remind us of a vital truth. Computer science is an ethical, responsible, and human-centered practice. We can't just shrug and blame the machine if it crashes into something or makes a bad choice. The responsibility lies directly with the programmer. We, the human engineers, have to take ultimate responsibility for how our automated systems behave out there in the real world.
This is exactly why, when uncertainty hits, we must step in with a human evidence check. And this is a simple three-step process. First, you need to constantly monitor your sensor data streams for any anomalies. Second, you run proper Arduino debugging fundamentals to check your hardware wiring and your code logic. And third, relying on research from the Carnegie Mellon Robotics Academy, we engage in what's called human-robot teaming. For a 7th grader, human-robot teaming might just look like carefully watching the serial monitor on your laptop screen while your robot runs an obstacle course. You're verifying that the scrolling numbers actually match the machine's choices in real time, just to ensure it's operating exactly as you intended.
Finally, let's look at Section 4, Transfer to the Real World.
The concepts you are learning right now, they aren't just for the classroom. They are actively driving the global aerospace and tech industries. NASA's Lunar Surface Technology Program tests complex wheel mobility designs for future lunar rovers using these exact input-to-output loops to navigate extreme dust and harsh craters. Over at the Carnegie Mellon Robotics Academy, they're programming autonomous drone swarms to fly in formation using these identical algorithms. And these principles are the very foundation for Edge AI, which simply means the robot's brain processes the data right there on the microcontroller itself, rather than needing to send it over Wi-Fi to some massive cloud server. The scale of the robots changes drastically, for sure, but the fundamental sensing logic you're mastering right now remains exactly the same.
Thank you so much for joining me for this explainer of our lesson. You now have the tools, the evidence, and the reasoning frameworks to build some truly incredible automated systems. But as you step back to design your own algorithms and deploy your own models, I want to leave you with this one thought. How will your human oversight shape the robots of tomorrow? Thanks again for watching Sensing, Application Task Video Overview, STEM, Robotics-STEM-Robotics-Unit 04-Lesson Pack 03-Sensing Application Task Video Overview.